Hello everyone, thank you for assisting my presentation about mixed finite elements for Kinking analysis in orthotropic media. First, as a summary, I'll present the introduction followed by the definition of the mixed finite elements of the study, the Reisner's modified quadrilateral finite element, then the computation of the energy release rate, and the orthotropic elastic constant, next the Kinking crack, and of course a numerical example taken from literature, and lastly the conclusion. First, as an introduction. As it is mentioned in the title, this work is about an investigation of crack within an orthotropic media. Those orthotropic materials that are often known for being characteristic for materials such as wood are also known for having different mechanic behavior along three orthogonal axes. For this work, the fracture will be considered as to extend in a direction oriented with a defined angle. Then the energy release rate will be calculated using two methods, which the results will be compared side by side. And this whole work will be illustrated using a special finite element, the Reisner modified quadrilateral finite element. So, what is the Reisner finite modified quadrilateral finite element? It is, in fact, three elements that have the Reisner element as a parent element. Those three elements are named the RMQ7, RMQ11, and RMQ5, RMQ11 and RMQ7. The number following the abbreviation represent the number of nodes. So RMQ7 is when we start from the parent element and add a displacement node. Then with the direct location we will get the RMQ11. As followed with static condensation, we will obtain the RMQ7 with 7 nodes. This RMQ7 with 7 nodes can have 5 displacement nodes and 2 stresses nodes. In one facet, the facet that are shown below, they have 3 displacement and 2 stress forces, which allow us to be sufficient for represent a fracture problems. When this facet is directed to the crack lips. Okay, we will have now to describe the displacement component. The displacement component is described by this equation. The U is which is global displacements is equal to n matrix n is the matrix of interpolation for displacements, and Q is the nodal displacement. Next, the shape functions on the matrix of interpolation are as follows. Once we have the displacements, we can second do the stress field. The stress field has this equation sigma, which is the global stresses and for the global stresses, is equal to the matrix interpolation for stresses m. M is multiplied by tau. Tau is the nodal stresses. The shape functions to estimate sigma 1 are as follow, and the shape function to calculate sigma 1 2 and sigma 2 2 are as follows also. For this element, we can now show the stiffness matrix of the element. The stiffness matrix of an element K, E is for element, will be equal to the assembly of K sigma sigma and K sigma U, where K sigma sigma will be dependent of the height, the matrix of interpolation for the stresses, and the stiffness matrix K sigma U now will be dependent of the height H, and the matrix of interpolation and the matrix of strain displacement B. Now we can calculate the energy release rate. We have two methods of computing the energy release rate: the crack closure integral and the stiffness derivative procedure. First, the crack closure integral. The crack closure integral have an idea that for a crack to be opened by delta L, the same energy to open a crack is the same energy to close it. So when we take a crack that is opened with in delta L, then the second step we measure the stresses and the energy to calculate the closure of this crack. It have these equations. This equation can be simplified to this, where sigma this index is 1 and 2. 1 represent the first step, which is the stresses, and second is the 2 is represent the opening, displacement of the once the crack is opened. For the finite element, for the representation on the finite element, we have nodes when it is closed. The nodes 1, 2, and 3, and 4 will have submitted the forces, the nodal forces. And the second step, once the crack is opened with delta L, we have this displacement, delta V, delta U, where of the nodes 5, 6, and 7, and 8. So the same equation as before can be written as this, where the stresses will be represented by the forces F of the nodes, and displacement will be represented by the displacement of the nodes. The sum of these two, G1 and G2, will be the total energy release rate. Second, the second technique is the stiffness derivative procedure. The stiffness procedure starts with the global energy for the system. Have two terms. The first terms and first parts will be dependent of K, the stiffness matrix, and the second part will be dependent of the forces, and both will be dependent of the displacement. Once we derive it by dl, the extension, we'll have this term. It's only the term that is dependent also by L, by the extension. As it's written on the previous work of Bouziane 2014, this is the exact writing. It's the sum of vector V is the vector of nodal displacement, dk by dA is the derivative, and the derivative of stiffness by the extension, and F is only the elements around the crack tip that are considered to calculate this energy release rate. Since there is a sum and decay delta, and there is derivative, we can consider two configuration. First configuration is M0, where the crack is not opened by the delta A, and the second crack is when the second crack configuration is M1, when the crack is opened with delta A. For the orthotropic elastic constants, we know that the orthotropic materials have material properties that differ along the orthogonal axis, which means that at x-axis have its own Young modulus, Poisson ratios, and shear modulus. For the stiffness matrix is expressed as follows. It is a 6 by 6 matrix where I have 9 components that are not null. We can once we study it in the two-dimensional problems, it will be reduced to a matrix of 3 by 3 where 4 are not null. For the kinking crack, it is simple. Once we have the where we present the crack, it is oriented by an angle. We'll only illustrate it and configure the element to have the same angle of the kinking. For the numerical example of this study, a plate with the weight of 2W and the length of 2L is taken into consideration. A crack at the central edge of this plate of A would have 1 millimeter. Then this plate is submitted to a traxial forces sigma. It also have a orthotropic mechanic properties. The results of the after are for each angles are presented in this table. This table have as the results from Mighty, the work of Mighty in 1986. The graph will represent the results, and first we have the stiffness derivative procedure, then the graph of crack-closetic integral, then the analytic in green. Results are green. We can see that clearly that those results are quite accurate. They are close enough to the analytic results. As a conclusion, the IMQ7 does illustrate accurately the fracture problem, of course, as this work shows, related to the kinking crack, with the consideration of the orthotropy of the material. And second, the energy release rate can be obtained by two techniques, where the first, the crack closure integral and the stiffness derivative procedure, show results that are close enough and accurate enough to the analytic results. Thank you for your attention. See you and have a good day.